This is going to be the Chapter 2 lecture regarding, or a lecture over problems 10 through 16. So let's take a look here. Derive the formula of lambda is equal to hc divided by E for the wavelength associated with a photon of energy E. So how do we come up with this? If we go to page 38 of the book, we can see this particular relationship right here. So we've got the wavelength times the frequency is going to be equal to the speed of light. We also see here that the energy of a photon is going to be equal to h Planck's constant multiplied by the frequency. So if we take this formula, and again, I'm going to go here to allow me to draw. So if we take lambda, I really wish it would default here. Lambda nu is equal to c. Take that and we solve that for nu. Get this. We take this, substitute it in here. We find that the energy is going to be equal to hc over lambda. Is that the same thing that we have here? Not quite. We need to solve this for lambda. So we're going to take this, multiply both sides by lambda, divide both sides by energy. That cancels. And essentially what all you've done is interchange the places of energy and lambda. So that's how we end up with that. So how do we derive equation 2.21 from that? Well, let's go and let's look at equation 2.21. Go here. You can see here that we just have a constant up here, 1.24 times 10 to the minus 6 divided by the lambda. Well, if we do that, let's try multiplying these two numbers together, which are given here. And again, I'm going to go to Excel. So we know that h in this case is going to be 6.63 times 10 raised to the minus 34th. We know that the speed of light is 3 times 10 raised to the 8th. If we take the two and we multiply them together, what do we got? Get 1.989 times 10 to the 25th. Now, does that match what we have here? Well, no, not exactly. So what are we going to need to do in order to be able to convert this? So what we're going to end up having to remember here is a Planck's constant is written in joule seconds. We've multiplied that by the speed of light. And so that gives us some odd little units here of joule seconds times meter per second. Now, that's not really going to help us that much in terms of trying to write this in EV. So the question is, what sort of change do we have to make in order to be able to get that huge number that I had there, which doesn't match what's on the screen, to match what is on the screen? So here's basically what we have to do. We are going to have to take this conversion factor right there. And you may or may not remember from the last video what that is from. And I'll go ahead and give you a reminder. Remember how 1 EV is equal to 1.6 times 10 to the minus 19th joules? Well, guess what? If we've got a unit, which we do, that is joules per second times meters per second, we're going to have to be able to change that from joules to EV. And that's the conversion factor that we're going to need. So now, if I know that this is the number of joules per EV, then if I take the number that I have here, which was basically the joule seconds, and multiplying that by meters per second, obviously the seconds here cancel with the seconds here, so I end up with joule meters. And since I'm dividing that by the wavelength, I would end up with just joules. So this essentially ends up with joule meters. And so if I take this and divide it by that, then I end up with EV times meters. That's essentially what that unit is up on the top. So that's where that comes from. And that's the answer here to part B. So what wavelength in terms of nanometers is associated with a 10 keV photon? So let's kind of clean things up here a little bit. Okay. So what wavelength? Again, what formula are we going to need to be able to use? This is going to tell us what the energy, or we know what the energy is, but this will tell us what the wavelength is. So basically we take this equation, rearrange it. So we end up with here, let's get the notation on. So here, lambda is going to be, let's try this again. Lambda is going to be equal 1.2. Now when this thing is on, it's really on, but when it's off, boy, it's really off. 10. Again, it breaks. 10 sixth. Of the energy. In this particular case, I have 1.24 10 sixth divided by 10 keV. Now remember that this unit up here, we're looking at EV meters. So we need to change this to EV in order to be able to get the correct comparison. So we've got this is equal again to 1.24 times 10 to the minus 6th EV meters. And then on the bottom we have 10,000. We shouldn't do this. Let's see. Because basically I'm taking this and multiplying it by 1,000 in order to be able to convert from KeV to EV. And I should have 4 zeros there. Okay. So now I'm going to take this, multiply it out, and I should get the wavelength at the very least in meters. So let's go to Excel. Okay, so there's my value. I'm going to take this and divide it by 10,000. And that is my wavelength in meters. How many nanometers is that? Well, let's see. What did they ask for here? Yeah, it's in nanometers. So the question is, how do I change that to nanometers? Well, the nanometers, if I were to express this, would be this. Let's see. 10. That would be in nanometers. I take this answer, multiply it by 10, and I should end up with 0.124. Yeah, in other words, this should be basically I would have to move that decimal point over. And it's not really easy to see here. Basically, if I take this and yeah, I'd end up having to divide. Yeah, because if I move it over one place there and then reduce the exponent, then yeah, that would do it. So basically, I am taking that, moving the decimal place 1 over to the left, and that would be the same thing as the number of nanometers that I have. A little bit less clear than what I would like. Let's see, so if I could write this over here. Two, 4, 10. So if I want to take this and I want to convert this into nanometers, essentially what I'm going to end up doing, that's kind of difficult, I guess, to see a little bit, is essentially I want to take the decimal point. If I move it over here, then that gives me, and that's what I was failing to do over there on the left side. And 10 to the minus 9th is the same thing as saying nanometers. That's pretty much where that answer comes from. So made it through 10C. How does this wavelength compare to the size of the atom? Let's just take a quick look here and see if it gives us the same order of magnitude. If we look up the size of the atom, roughly that's about where we're going to end up. And let's see, I don't know if it actually lists the size of the atom here. It might. Maybe there's an electromagnetic spectrum. Yeah, it doesn't really say here. I was hoping that it would, but anyway, that's if you look at the size of the atom, that's about what you're going to be looking at. Okay, give the SI units for the following quantities: frequency, wavelength, power, energy. Let's see if there is at the front here, if that table actually gives us the information we're looking for. Doesn't really tell us there in the table, does it? Okay, well, let's go to spectrum. Okay, you can see the SI unit here is the hertz for frequency. For wavelengths, you're probably looking at something with nanometers. Power, again, is going to be joules. I'm sorry, power is going to be watts. Energy is going to be joules. For problem 12, write the following list of types of electromagnetic radiation in order of decreasing wavelength. If you go here to 12, you can see this. This also matches up. Let's see, we should have it here. You can see them listed here. So you can see the wavelength, it increases going this way. Radio waves are really, really big. Gamma rays are really, really small when it comes to the wavelength. So you can see here, again, the order is going to be decreasing wavelength. So you're going to be going from the biggest to the smallest. So radio, microwave, infrared, visible, UV, and X-rays. So as you're going here, the wavelength is getting smaller and smaller as you go through here. Is the energy increasing or decreasing? Well, energy increases. The reason the energy increases is because here the frequency is getting bigger and bigger and bigger. And what do we also remember about how frequency plays into energy? It's basically a positive number multiplied by the frequency. So the bigger the frequency, the bigger the energy. So that's why the energy increases in that direction. Number 13, describe briefly in words the nature of an electromagnetic wave. I will leave that for you to be able to do, but if you read through this particular chapter here, you can see here, you can pick up on the fact that light is going to end up being a packet of energy, which can behave as a photon, it can behave as a wave. And it's a pretty interesting reading there to go through it, determine all of that. Compute the frequency and the wavelength of a 100 keV photon. Well, to do that, you've got the energy here, which you can substitute in. And remember, that is in keV. So you'll want to convert that to EV. Use this particular relationship, and you'll come up with a number of meters. Once you've got this, you can plug it into this particular formula, and you can figure out what the answer is. So let's just kind of go through that. 100 keV. So here. All right, so we've got, let's say, it said 100 keV. This is the same thing as multiplying this by 1,000, so I should end up with 100,000 EV. So basically I've got 100,000 EV, which I can put here. I can rearrange this formula to give me this is equal to 1.24 times 10 sixth divided by 100,000. So to do that, if I go here, that should actually be 1.24 times 10 to the 6. So that's what I end up with. How many nanometers does that come into? It's just asking us to find the wavelength. I'm not sure it's specified exactly which unit to use. Doesn't, but it does say 1.243 times 10 to the 11th meters, which is exactly what we've got here. So to find the frequency, I'm going to take, again, I think I jumped the gun here, sorry. Let's go. It's not letting me do this. I'm going to take this formula, and so I can find from here that frequency is going to be equal. Well, technically you can do this one of two ways. You can do it this way since you found the wavelength here. You can determine that this divided by this is going to be the frequency. Another way is that if you know what the energy is, which we do, it's 100 keV, you can plug it in here, divide by Planck's constant, and you can determine the frequency. Either way is going to be good. Kill that, and then go here. So I've got this. So I've got the speed of light divided by this. Coming up with something that's very, very big. Is this correct? 2.4 times 10 to the 19th hertz. Yep, indeed. That is indeed it. Okay. So it's the speed of light, 3 times 10 to the 8th, divided by the wavelength, 1.243 times 10 to the negative 11th meters. And since this is in meters per second, this is in meters, then the meters cancel, and I'm left with basically something per second, and that's hertz. Okay. All right, so let's go to the next one. So number 14, we have here. Looks like it's the same process. We're going to take, we know what the wavelength is, and we can determine the frequency, again, by using that same formula. So if we take so we know that C is equal to lambda nu. If we know what the frequency, or if we want to know what the frequency is, take C, which in this particular case, I believe it said we have a wavelength of 6 centimeters. So how do we change that? What do we do? Well, again, I'm going to take the speed of light, which is here, and I'm going to divide that. Now, you got to be careful here, because if the speed of light here is measured in meters per second, if you divide by 6, then essentially you're dividing by centimeters. The units aren't the same. So I basically want to convert that 6 centimeters into 0.06, and the reason is that gives me the number of meters. So this is going to be the hertz. So, correct? 5,000 megahertz. Is this in megahertz? Well, obviously this is in hertz. If I were to change this and put it into megahertz, I would take it and divide it by, well, mega is going to mean a million. And indeed, come up with 5,000 megahertz. Okay. All right. Now, what band of the electromagnetic spectrum is this in? Let's see here. More or less probably microwaves. And the reason I say that is because 10 to the minus second meters is going to be about 1 centimeter. And indeed, that's what it says here. Okay. All right, we got 2 more to go. Not too bad. We can get through this. Hopefully you haven't completely tuned out by now. I hope so. Hope that's not the case. Okay, so now let's go to this problem right here. 15. A tungsten atom is ionized by ejection of an L shell electron. How much energy is required? Okay, there is in the book, let's go here to what is radiation. Yep, that took us to the problems. Very helpful now, is it? Let's see. There we go. Now we're getting into this area here. And let's see if we can get down to discussion here. Okay, this is our tungsten atom right here. Tungsten. So the question is, tungsten atom is ionized by ejection of an L shell electron. How much energy is required? If something is in the L shell, you've got binding energy here of 11 keV. If you're going to take something, you're going to pull it out, then guess what? The answer is 11 keV. Is that what I said here? It should be 11 keV. I don't know if I mentioned the keV word. What is the value of the quantum number n? In other words, what quantum number is associated with the L shell? Well, let's take it back. These are your quantum numbers right here. So when n is equal to 1, that corresponds to k. When n is equal to 2, that corresponds to L. That's why they say n is equal to 2. All right, so an electron makes a transition from the L to the K shell in tungsten. What is the energy of the emitted photon? Well, again, let's go back to, okay, so it said we're transitioning from the L to the K shell. What is the energy of the emitted photon? So we've got an electron that's jumping from here to here. So when it jumps from here to here, we're seeing a difference here of 70 and 11, which ends up being 59 keV. So when an electron makes a transition, basically it's pulled from the L shell into the K shell. Maybe there's an opening here or something like that. It took 11 keV to hold it here. Now it's going to take 70 keV to hold it here. So when that happens, the energy difference between the two is what is going to be transmitted to the emitted photon. In other words, because the it's going to pull it in, it's going to accelerate that electron. In order for it to stop at that particular point, um, it's going to have energy that goes from the 11 to the 70. Now, when it does that, the electron's in orbit there, and it doesn't need that additional amount of energy. It gets released in the form of a photon, and that photon is going to have the energy of the difference in those energy levels. So it's going to be from uh, 70 minus 11. So in other words, that extra energy can be thrown off into a photon somewhere, and that's what it's talking about. What is the wavelength of the photon? So to find the wavelength of that particular photon, again, we're going to go back through the formula that we had before. Let's see, I don't think it's on this page. I think it's did I say the wavelength of the energy? What is the wavelength of the photon? Okay, go back to here. We put in the energy of the photon here. We go through and basically exchange the places of lambda and energy. So I'm going to take 1.146 or 1.24. I don't know why I said that. We're going to take that, and the energy of the photon was 59 keV, or I need to express it in EV, so it's 59 there. So if I take this and divide it by this, come up with 2.10 times 10 to the 11th. Is that in fact what we have? Yes, if I take this and I move the decimal point 2 points over, basically I get 0.021. Again, this is going to be in meters. This is going to be in nanometers, which basically means I take this right here and divide it by 100 in order to be able to get this to reflect nanometers. This becomes the nanometers. And that does in fact correspond to the X-rays because, again, if you look at the electromagnetic spectrum, eventually, you'll see here, this is the same as nanometers. So actually what we're looking at is even shorter than that. So that is where this comes from. So hopefully this gives you a little bit better idea as to how these problems are solved, and then you can work on the homework, which is very much a reflection of these, and you can kind of see where the answers are coming from.